Hello, everyone. So this is going to be the second lecture for Kinesiology 376. In this lecture, actually, I shouldn't say lecture. This is going to be the second half of the first lecture. I'm probably going to mess that up a whole bunch of times just because I'm doing this from home and I'm trying to do them all in order. So if I keep messing it up, I'm sorry, but I will try to get that straight. But otherwise, this is the second part of the first lecture. Okay, so this is the second PowerPoint presentation of the whole class. Okay, so in this lecture, or in this presentation, we're going to do a bit of a review of the math you'll need for this class. We won't get too much into the physics, that's saved for our kinematic and kinetic lectures, but we're basically going to be looking at some of the common trigonomic functions you're going to be using, our units of measure, which we're going to get into just a bit, and then just kind of the basic algebra. But first off, in biomechanics is a science. That means we use metric. The US uses the imperial system, sometimes called the English system. We are one of the few countries in the world that still uses the imperial system. I think it's us, Burma or Myanmar, and actually sometimes the UK whenever they feel like it. Sometimes they use the imperial system for speed, but then they use stones for weight. But sometimes they measure everything in meters. The UK is just weird like that. They can't decide exactly what they're going to do. But besides them, the rest of the world uses metric. Metric is different. Metric is a unit of measure that makes sense. When I say makes sense is everything is either divisible or a multiple of 10, with the exception, I guess, of temperature. But when we look at that is we know that there's 1,000 meters in a kilometer. There are 10 centimeters in a meter. There are 10 millimeters in a centimeter. So it makes everything a little bit better. There are roughly, or not roughly, there are exactly 1,000 grams in a kilogram. So we like to use the metric units, the metric system of measurement. It just makes much more sense and kind of makes everything a little bit less confusing. So in this class, excuse me, I got a little bit of a cough today. But for this class, what we're going to be using is all metric. So, and unless otherwise specified in the classes, you'll be working with metric units. If the question is asking you to calculate something and it's not in a metric unit, you are required to convert that unit to its metric equivalent. And we'll go over that a little bit today. So in this class, almost all your answers, you're going to have to use metric unit. Okay, I'm re-recording this slide because I accidentally clicked through it and PowerPoint doesn't let me go backwards. So what I'm getting into is we're using metric, okay? One of the important units in metric and in this class is newtons. Newtons is defined as a force which gives an acceleration to a mass of 1 kilogram. We call it a newton because it's from Isaac Newton. You guys probably remember him as the guy who was sitting under a tree, had an apple hit his head, and thus discovered gravity. We knew about gravity before him. We knew well before him. We knew about, we knew that the earth was round well before him. We knew the earth revolved around the sun before him. We knew that there were other planets in the solar system before him. However, Isaac Newton was the first person to take all of the knowledge we already had and refine it and kind of, for lack of a better word, perfect the mathematics of it and put it all into one place. Okay? If you are ever thinking that you're just the smartest person in the world and nobody can ever tell you something you don't know, remember, Isaac Newton developed calculus before he was 30. If you have never heard of calculus, calculus is the bane of everybody that's gone to school and for any type of science. We all have to take calculus, and the first time you see it, you're kind of amazed. Isaac Newton developed it, wrote all the rules of calculus before he was 30 years old. He also wrote a really, really big book about all the fish in the world because he's that kind of guy. He just likes to write books. But he developed the rules of physics, or at least classical physics, before anyone else. Okay, he developed the calculus to explain how the Earth revolves around the moon, or revolves around the sun, sorry. Does not revolve around the moon. He was able to explain how gravity actually works. We knew about it, but we weren't able to really understand how it worked before him. So we decided, well, he came up with all this stuff. So the unit of force will be called a Newton, okay? And a Newton is a force. 1 Newton gives a force, okay? And that force gives an acceleration of 1 meter per second squared to a mass of 1 kilogram. If you need the conversion, 1 kilogram is about 2.2 pounds, okay? And we'll talk about why that's important in just a bit. But what you'll see in just below that is an equation. It says F equals ma. We will talk about this more when we get to our kinetics and kinematic stuff. But it's saying force is equal to mass times acceleration. Okay? This is an incredibly important equation. This is the second law of motion developed by Isaac Newton. Basically what it's saying is for something to move or stop moving, if we take an object, any side of object at all, another person, an apple, a bowling ball, whatever, we're saying that for us to move it, a force has to be applied, okay? And while it's moving, that movement is called an acceleration, okay? An acceleration is a change in velocity. Velocity is not speed. Velocity is a vector. A vector has a magnitude, which would be speed, and a direction in which it's actually moving. So what we would say is if an object, let's say, is at rest, it's not moving, it has no velocity, or has a velocity of 0 and an acceleration of 0. The same is true if it's moving at a constant velocity. Let's say you're in your car and you're driving down the freeway heading north at 65 miles an hour. Your velocity is 65 miles per hour north. Your acceleration is 0. If you are going in the same direction at a constant speed, you have 0 acceleration. If your acceleration changes, you either change your direction, you were heading north, now you're heading east, you change your magnitude or your speed, you're going 65 miles an hour, and now you're going 70 miles an hour, you sped up, or you're slowing down, you were going 65 miles an hour, now you're going 50 miles an hour, then there's an acceleration because you have changed your velocity. For that acceleration to occur, a force must be applied. For you speeding up, that force was the force of combustion of your engine as you press down on your gas pedal harder. Or if you slow down, that's the force of friction on your wheels applied by your brakes to negatively accelerate you, okay? And we'll get into more of this as we go on. But force equals mass times acceleration. This is important here. In the imperial system, the silly system we use here, the one that is just silly, the unit of force is a pound, okay? In metric, a kilogram is a unit of mass. So when we convert pounds to kilograms, you are converting a force to a mass. If we want a force, though, we have to apply an acceleration. So we see here is 1 kilogram is just the mass. If we apply the acceleration of 1 meters per second squared, we get 1 Newton, okay? So remember that. A kilogram is a mass, and a pound is a force, okay? Just keep that in mind when you have to convert your units. So pounds and kilograms represent two very different concepts. So when we're converting our factors, we need to know some stuff. Right here and in your exams, everything like that is I mentioned in the videos, I'm giving you conversion sheets, I'm giving you the equations so you don't have to memorize this stuff. Okay? But 1 inch is 2.54 centimeters. 1 foot is 30.5 centimeters. This is very easy to do. How many inches are in a foot? There are 12 inches in a foot. If you multiplied 2.54 times 12, you'd get 30.5. In a yard, there's 91.4 centimeters. At a certain point, this becomes a little silly, okay? So what I'd suggest, okay, if we're looking at this, is no, an inch is 2.54 centimeters. You can get anywhere else from there because you know there's 12 inches in a foot, 3 feet in a yard. So you'd take 1 times 3 times 12, okay, would give you 36 inches. Multiply that by 2.54 centimeters, you'd have 91.4 centimeters, okay? That's 1 yard is approximately a meter, okay? That little squiggle means approximately. And so 1 mile is roughly 1.609 kilometers. The beauty of the metric system is if we wanted to know what, how many centimeters that is, we know that there's 1,000 meters in a kilometer and 100 centimeters, or yeah, 100 centimeters in a meter. So we could just do the math out that way. It would be much more simpler than having to convert everything. Also, when we look at a pound, it's roughly 0.54 kilograms. I find it's just easier to know that there are 2.2 pounds in a kilogram. This is also important. Significant digits are important. If you don't think they're important, look at all of the mistakes NASA made when they were just learning to build rockets. Same thing with units. Is there a lot of rockets that blew up because somebody didn't use the right unit or their significant digits were off in their calculations, okay? It's very, very important that we have a standard. So when you're doing your homework, when you're answering questions in an exam, know that in this class, we report our answers to 3 significant digits, okay? So we're going to do a little bit of practice here, okay? So 0.333 repeating, when I say repeating means it's going on forever, okay? If we're reporting to 3 significant digits, we have 0.333, okay? The same goes when we say 5.3 repeating. The 5 counts as a significant digit. So what we'd report is 5.33. This is important too when we consider if we're rounding an answer, okay? if the digit following the last significant digit is between 0 and 4, the last digit remains as it was. So we saw here 5.33 repeating, okay? The last significant digit is this fourth. I'm going to try to circle it. This, now I obscured it, but know there's a 3 behind that. That fourth 3 is between 0 and 4. That means the 3 before it remains a 3. However, when we look at this next one, 74.564, this fourth digit right here, this 2, is also below 5 is what we're really saying, but it's between 0 and 4. So that 4 is that 4 is not going to stay because we already have 74 is 2 significant digits. So it's going to be 5. What I should have said, is this 6 right here, I covered it up again, is greater than 5. So we increase that 5 by 1. So then we report 74.6. So let's look at this next one, 24.48432. Okay, we're reporting to 3 significant digits. All right, after the last significant digit is 8. Okay, 4 is where significant digits end. So 8 is greater than 5. So we'd increase that 0.4 to 0.5 and then report 24.5. And this continues on and on and on. Now, we do not consider any number with leading zeros or 1 to be significant. So when we look at this one, 0.3678, we take this 8 because that's the significant digit, or that's the end of significant digits right here. The 0.0367, the 367 is our 3 significant digits. So we take that 8, it's greater than 5. So we take 7 and increase it by 1. So now it's 8. So we're left with 0.0368. And we do the same here. Okay, the 562, okay, those are our 3 significant digits because there's 2 leading zeros before it. Now, the last one, 2, is less than 5, so we don't increase the significant digit before it. Okay, just keep this in mind when you're answering questions on the exam, when you're doing homework, is we're always rounding up past 5, okay? And we're always reporting to 3 significant digits. Now, I already said this, but we'll kind of go over it one more time. Leading zeros and 1s do not count as significant digits. So we have 0.133 repeating, okay? That's going to have 4 total, or technically 5, but 4 numbers after the decimal point because it's leading with a 1. So this 1 right here doesn't count as a significant digit. We have to count for, let me try the blue here, 1, 2, 3. Those are our significant digits there. So we actually have 0.1333, okay? Let's look at the next one. 1.3 repeating becomes 1.333. This right here is our leading 1, all right? It's not that hard. It's a little confusing, but it's not that hard. So we'll make it a little bit harder. We have 14.56421. Do we have a leading 1? Yes, we do. So this right here is our leading 1. So we're not going to consider that. So we still need 3 significant digits. So that's going to be 4.56. 4.56. Okay, so that's going to give us 14.56. All right, so now we have 14.48432. By the way, it gets boring when I start shouting numbers, and I'm shouting numbers in my apartment right now, so I'm wondering what my neighbors are thinking right now. But we have a leading 1 again. So what is our answer? It's 14.48. We have a leading 1, and we still need 3 significant digits, so that's going to be 1, 2, 3. The last one is not greater than 5. It's not 5 or greater, so we get rid of it. I'll use red here. We'll get rid of this. Okay, so it's going to be 14.48. Next one, we have 0.016783. Okay, we have 2 leading zeros and a leading 1. So what can we do? It's going to say exactly the same because we have, get this, we have 2 leading zeros and 1 leading 1. So those don't count. All right. So we still need our 3, I'll try green. We still have our 3 significant digits here. We're just getting rid of the 3. Oops, that was supposed to be red. The 3 here. Okay, so we have 0.01678. If that 3 was a 5 or greater, it would be 0. It would be, I'll just write it out. It would be 0.0168. It's hard to do on my laptop screen, but it would be 0.0168. All right, so let's look at this very last one right here. 0.016225. We have 2 leading zeros, 1 leading 1, and then we have 1, 2, 3 significant digits. But, try a different color here. This number, 5, is equal to or greater than 5. So we have to round up the 2 preceding it, the number 2 preceding it. So we're going to be left with 0.01623. We have, this doesn't count for a significant digit, this doesn't count for a significant digit, nor does this. Here are our 3 significant digits, 6, 2, 3. We increased that last 2 by 1. Okay, so kind of clicked a little bit ahead there. But when we're converting units, you need a reliable method to convert one system of units to another, or to convert units within a system. Okay, so we have kilometers per hour, meters per second. We very rarely say kilometers per second or meters per hour. We use it from time to time, but in this class, these will be kind of integral. Okay, so we're going to look at an example. We're going to convert 100 kilometers per hour to miles per hour. There is a good way, and I suggest you guys use this whenever you're doing any of your math. The first step you should take, write out the number in units, okay? When you're doing any of the math for this class, the units help you solve the problem. If you use the units consistently throughout all of your work, there's less of a chance that you'll get kind of lost looking at all the numbers. In fact, what I like to do, especially if you need the practice, is don't use numbers when you're practicing. When you're practicing for this stuff, if you've gone through, I mentioned it in the first video, the introduction video, that's not a PowerPoint slide. that if you need a refresher on this stuff, look at the Khan Academy. If you look at that stuff, he uses the numbers. What I'd suggest is when you're doing your stuff, don't use numbers. Just use the units. If you're just using units, you can solve the entire equation, and then all you have to do is plug in your numbers in your calculator, replace your units with numbers in your calculator, and you've solved it. Okay, you just plug and chug it away. So write out the units, write out your numbers in units, but make sure you use your units because they will kind of guide you to how an answer is going to be solved. And write them out in kind of, a horizontal format, okay? So kilometers per hour here, we want to write it out. This sounds weird to say horizontal because that's technically horizontal, but we'll write it out like this, okay? If we do it like that, it kind of helps us solve and kind of visualize what we're looking at. We're looking at kilometers per hour. So kilometers divided by hour. So we're doing this one, we're doing 100 kilometers within 1 hour. So that helps us kind of solve this. So determine the ratio of units you are converting, okay? That, by writing it like that, you're helping to determine that. Then you're going to multiply the ratio of the units you are converting by the ratio of the units you are converting to, okay? So 1 mile is roughly 1.609 kilometers, okay? This converts to a ratio. Oops. This converts to a ratio. So we're looking at 1 mile equals 1.609 kilometers, okay? So we're saying that within 1 mile, there's 1.609 kilometers. Or you could say it reverse, okay? Here's the great thing about writing it kind of in the format we do. We have 100 kilometers per hour times 1 mile over 1.609 kilometers. Does that make sense? Or does 100 kilometers per hour times 1.609 kilometers over 1 make more sense? This is a little bit of, it takes a little bit more math sense, but you got to look at which we need to get rid of kilometers. So how can we cancel them? The first one we can cancel them. They're cross products, so we cancel them. Okay, so we're going to use that first one. So this way we can cancel out their cross products. We can cancel out the kilometers per hour. And so we have 100 times 1 mile. So it'll give us 100 miles per hour. Okay, so this will go back over here. All right, and then we have 1 mile over 1.609. That gives us 62.2 miles per hour. So always look at your units. If you can't cancel them, you just made a mistake. You just got to go back and resort your denominator or numerator. So now let's convert 100 miles per hour to kilometers per hour. We already did this. 100 miles per hour. There's this. 100 miles per hour times 1.609 kilometers per mile gives us 160.9 kilometers per hour. Hopefully that made sense. Now let's convert 5 centimeters to inches. We know from the previous slide that there are 2.54 centimeters per inch. Okay, so we'd multiply 5 centimeters times 1 inch, then divide it by 2.54 centimeters, giving us that 5 centimeters is equal to 1.969 inches. One thing to look at right here is this answer has a leading 1. So we still have 3 significant digits here. Fourth one, we can convert 25 meters to inches. So we have to convert meters to inches. We know there's 100 centimeters in a meter. So there's 100 centimeters in a meter. So we multiply 25 meters times 100 centimeters. Okay, that would give us roughly 250 centimeters. And there's 2.54 centimeters to 1 inch. So we divide 250 divided by 2.54 gives us 989 inches. Still 3 significant digits. So we're going to convert 25.0 kilometers per hour to meters per second. I'm going to pause the video, and I suggest you do as well, and see if you can solve this by yourself. Okay, so I paused it. I hope you guys solved it. So let's kind of go through this here. We're converting 25 kilometers per hour to meters per second. So we need to do 2 things here. We need to convert kilometers to meters. There are 1,000 meters in 1 kilometer. So the first thing I would do is I would convert kilometers per hour to meters per hour. Okay, so I would just multiply 20, because I know there's 1,000 meters in 1 kilometer. I would multiply 25 kilometers by 1,000. Also, I know there are 60 seconds in a minute and 60 minutes in an hour. So I would multiply 1 hour by 360. Okay, so that would give us, we're going to convert this now. We have 25 kilometers per hour. I'm going to multiply it by 1,000 because there's 1,000 meters in a kilometer. Then I'm going to divide that hour by 60, and there's 60 seconds in a minute. So I'm going to divide it again by 60 seconds. That would give us our 360. Our kilometers are going to cancel. Our hours are going to cancel here. And then our minutes are going to cancel. So that's going to be equal to 25,000 meters over 3,600 seconds. This is ugly. We can get rid of some of this stuff. So if we divide it out, it gives us 6.94 meters per second. Okay, so now that's converting stuff. It's the simple stuff. This is more, hopefully, not too hard stuff. Algebra. We're using algebra to solve, most likely, for x. You will have some questions in either homework, assignments, and your exams where I'm asking you to solve for x in some way. That's because we have an unknown quantity somewhere. Okay? So for my first example here, x minus 5 equals 10. I need to determine the operation that will isolate the unknown variable on one side of the equation. Okay? X minus 5. So I need to get x by itself. I can do this. Why don't I just add 5 here and another 5 here? 5. There we go. The other one is just messy. Okay, so if I do that, I will have x equals 10 plus 5. This will cancel out here, and then I'm just adding. I actually put multiply, or I just had a sloppy plus sign. So I'll have that. So then x equals 15. Hopefully that makes sense. Remember, if you're doing one side, if you're doing something to one side of the equation, you're doing something to the other. Okay? So you isolate the unknown variable on one side of the equation. by applying the same operation to each side of the equation, and then we solved it. So if we know that x minus 5 equals 10, that means x has to be 15. So let's look at some examples. Okay, I'll do the first 3, and then I'll pause it, and hopefully you can do the last one. 10 plus x equals 3. So I need to get x by itself. So why don't I just subtract 10? Sorry, that's a mistake in the middle there. It's not 1.0, it's 10. Subtract 10 from both sides, so that gives me x equals 290. So now we have 5x equals 25. Basically, what we're saying is 5 times x equals 25. The opposite of multiplication is division. So I'm going to divide by 5 on both sides. So we're going to have x equals 25 divided by 5. We know that's equal to 5. We know 25 divided by 5 is 5. So x is equal to 5. Does that work out? Does 5 times 5 equals 25? Yes. Okay. So now we'll do this fourth example here. X divided by 4 equals 36. Okay, so we have a division problem. We need to get x by itself. The opposite of division is multiplication. So pick a different, we'll just do it in black. Okay, so the opposite of division is multiplication. So if I multiply, whoops. Sorry, my computer is acting up. If I multiply by 4, sorry, my pen is acting up here. By 4 on each side, the little dot is my multiplication. By 4 on both sides, I get x equals 36 times 4. Okay, so what is 36 times 4? Should have done this ahead of time, but I didn't. It's 144. So then x equals 144. Okay. If basically we're saying, well, if x equals 144, we divide that by 4, it's going to be equal to 36. Okay. So this last one, I'm going to pause the video. I hope you do as well, and figure out what x is there. Okay, so hopefully you solve this. But we have x squared equals 9. So the opposite of squaring something is taking its square root. Okay, we do the square root thing. Okay, so let me get a different color here. How about green? All right, so we have x squared equals 9. So we need to get x by itself. So we'll do this. We'll take the square root of x squared equals the square root of 9. Okay, we know the square root of 9 is 3. 3 times 3 equals 9. So then we know that x equals 3. If we multiply 3 times 3, we get 9, or we square 3, that's 9. And then should have shown you all this before, but we'll just kind of go through this. All right, that gives us our results. All right, so now we're going to do a bit of trigonometry. I know, it's fun. Homer is having so much fun. All right, trigonometry is a branch of mathematics that deals with the relationship between sides and angles of a plane or triangle. This is important, especially when we start looking at some of the physics we're going to do here. If we're looking at how a muscle pulls on a bone to cause movement, every time we try to solve something like that, we're essentially using a right triangle to do this. When we're looking at the approximate distance a ladder should be placed from a wall so that a person can climb it safely. We're looking at a right triangle. If we're looking at the maximum knee flexion of a hockey player during skating, we'll draw a right triangle over that and use trigonometry to solve this stuff. What is the trunk angle of an injured worker? This is kind of important, especially when we look at lower back pain, is you very rarely see somebody with lower back pain that isn't kind of bent forward at their waist. If you've seen somebody sitting in an office chair, which I'm doing now, and because I'm doing this on a kind of small laptop, I'm kind of hunched over the laptop a bit, so my back is not going to thank me later. But generally, our back is kind of, or our trunk is kind of angled forward over our hips. That's going to place more stress on our lower back. And we could figure out exactly how much stress that would be by solving the triangle that it's creating. Okay, so that's why we use trigonometry. We use trigonometry to resolve the forces into different components. Okay, so we have here, I won't get too technical, but this right here is our triangle. Okay, this triangle has three sides. We have our hypotenuse, the adjacent side, supposed to be an A, and the opposite side. Okay, when we look at our forces, these are our vertical force, our horizontal force, and then the resultant force. Okay, that's how we use trigonometry. If we're looking at a person on the ground, I'm just going to draw something. Let's see if I can delete this stuff. I can, cool. See all my chicken scratches. Okay, let's look at this person on the ground. Okay, let's say I want to determine which way this person's going to move. Okay, I know that the spurt will assume this guy's on Earth. So we have the force of gravity. Okay, we'll call it, just for the sake of doing it, we'll call it G for gravity. And it appears like this person is going forward. We'll draw the vector forward like this. So we'll just call this F for forward. Okay, so we have a vector going to the right and a vector going down. Okay, so that means that they're going to do this. Ah. All right, so they're moving forward. This is our resultant vector. So then we have an angle here. This is always going to be a right angle. We have our secondary angle. I usually just say theta. Poor theta, what are you going to do? And beta. Because why not? Okay, that's how we solve most of our trigonometry functions in this class. Okay, this is where we kind of get into our using either sine, cosine, or tangent, or our Pythagorean theorem, a squared plus b squared equals c squared. So I'm going to draw one more thing. I'm going to get rid of this again. I only got so much room to work. I'm going to draw one more triangle. Get rid of all this stuff. Okay, I'm going to draw one more triangle. That is an ugly triangle. Let's try that again. All right, so this is my right triangle. All right, so we have a rule in trigonometry that we get to use all the time, which is Pythagorean's theorem, which is basically saying a squared plus b squared equals c squared. C is always the hypothesis or hypotenuse of a triangle. So that's C, and we have A and B. This B could be A could be B. This equals, let's say equals B equals A. This doesn't matter so much, okay? Which one's A and which one's B, which side is A and which side is B for this equation. We're adding them. We're adding them, so it doesn't matter. Oh, I was hoping that was going to be translucent. We're adding them, so it doesn't matter which one is which, but C matters. So if I square A and I square B and add them together, and then I take the square root, that will give me C. Okay? So we use all of this to resolve forces into different components. So how much force is applied vertically and horizontally into different movements. So we need to be able to calculate the angles and sides of a body segment and the forces and resultant movement. So kind of went over this already, but remember, our hypotenuse is going to be equal to C. We'll say for A. Opposite is O, but we'll say for our Pythagorean theorem is B. Okay, I switch around. I'm going to be probably switching around a lot. Usually when I write stuff out for trig, I have a different shorthand. I'll try to remember that. But usually when I say opposite, when I'm doing the work, I'll just have O, P, P for opposite, A, D, J for adjacent, and HYP for the hypotenuse. A lot of times that's how I learn, so old habits die hard. And last thing, remember that the inside angles of a triangle is always equal to 90, or to 180, excuse me. But in what we're working with is always going to be a right triangle. Okay, a right triangle means there can only be one corner in a triangle that is equal to 90. That means these last two, if we added, I'll use a different color, if we added these last two, they would be equal to 90 together. Okay, those two angles would also be equal to 90 because this one is equal to 90. 90 plus 90 equals 180. Okay, so in a typical problem, you'll know two of the following. Either this angle here, you know this one actually, so you'll know two angles. Because this one is always equal to 90, right? Because it's a right triangle. The length of the adjacent side to theta, this is our adjacent side right here. The length of the opposite side, right here, opposite to theta, or the length of our hypotenuse, right here, okay? Or we could have the length, the angle of, forgive me, I forgot what that symbol is. I'm just going to call it beta because that's only, I don't know much Greek, or this one right here, okay? If you know two of those, you can solve this entire triangle. You can solve H, you can solve A, you can solve O, you can solve the opposite angle. It's it's actually quite simple. You'll just use either a combination of or one of these different functions. You'll have sine, cosine, tangent, or your Pythagorean theorem, h squared plus a squared, or h squared equals a squared plus o squared, or you know how other people use it is c squared equals a squared plus b squared. Okay. When we have to decide between sine, cosine, and tangent, it's helpful to know that these are just trigonomic ratios. The sine of an angle, okay? So I'm going to delete some stuff to make some room. Delete. Okay. So this sine right here, or this angle right here, we know this one. We know the sine of this angle is equal to the ratio of the opposite length of the triangle over the hypotenuse. Okay, so that helps. So if you think sine, think so. Right here. So katoa. All right, so cosine of the angle is equal to the length of the adjacent side over the hypotenuse. Okay, and then finally, the tangent of an angle is equal to the opposite side over the adjacent side. Okay, so remember SOHCAHTOA. When I was still in, I don't know, middle school, I had a very eccentric geometry teacher, and she used to sing. So she used to sing a SOHCAHTOA song. So I won't sing it for you. So consider yourself very lucky that I'm not. All right, so let's do an example. When we look at this stuff, we have different steps in which we use this. Determine which equation has only one unknown variable. We don't like to make this work hard for ourselves, okay? We like to make it easy. So usually when we look at a problem, we can look at our equation, figure, okay, which language or which equation are we looking at that we have the information for every one of these variables except one. Then we can just resort the equation to solve for x, or the unknown. Then we just plug in the given values into that equation and solve for the unknown. There is one thing on your calculator. I'm trying to think if you're using your smartphone, if Apple does some weird stuff with degrees and radians. But make sure, you might have to kind of look that up because I don't use Apple. I don't know why anybody does. But if you're using Apple, just make sure that your calculator is set to degrees and not radians. We will be talking about the difference in later lectures, but just make sure that your calculator is set to the right units. And then just kind of keep determining the next equation that only has one variable, and then use that equation to solve for the unknown variable. It's just a whole bunch of steps. So let's look at this one right here. We're given two variables. We're given theta, and we're given the adjacent side that is equal to 35 centimeters. I need to figure out the opposite side and the hypotenuse, okay? So I have to kind of figure out, what do I want here? So let's look at our equations that are given. Obviously, I can't solve for the hypotenuse and opposite at the same time, but I can peck away at it. So I know A and I know theta. Okay, so I can do one thing right off the bat. I know A and I know theta. So why don't I use the cosine of theta is equal to A over H. Okay, so let's see how that works. Cosine of 35 is equal to 5 over H. And I just realized that for one reason or another, I put 35 instead of 5. I don't know, because my eyes did a thing. This is equal to 35 degrees. Oops. Degrees. Sorry, my handwriting's sloppy. Okay, so the cosine of 35 degrees is equal to A over H. A is 5. So we have this equation right here. So the cosine of 35 is equal to 5 over H. Now we need to get H, which would be our x, or our unknown variable, by itself. So if we multiply H to both sides, we get H cosine 35 equals 5. It's still not by itself, so we have to do one last thing. If we divide each side by the cosine of 35, we get H equals 5 divided by the cosine of 35. We do that, we get h is equal to 6.10 centimeters. So now we know 3 things. We know that theta is equal to 35, that A, or adjacent side, is equal to 5 centimeters, and we also know that h equals 6.10 centimeters. So now we only have one last thing to do. We could do 2 things, okay? We could either use the Pythagorean theorem, h squared equals a squared plus o squared, or we could use one of these trigonomic functions as well. But let's use tangent, because why not? We'll just make it a little bit tougher on ourselves. Okay, so we now have O or A and H. If we look at tangent, and we need to solve for O, this is the only one with O as the missing variable. So no, tangent of 35 is equal to O of 5. Okay, so if we divide by 5 or multiply by 5 on each side, we have 5. Tangent of 35 equals O. So O is equal to 3.50. You could have also used the Pythagorean theorem. In fact, that's what I would have done if I needed to solve for O. I could have just inserted H and A into the Pythagorean theorem and just solve for O that way. So what we were looking at before, we were getting kind of close to having to use an inverse trig function, okay? When your angle is unknown, you have to use the inverse trig function to solve for it, okay? If you're looking at your calculator, pull out your calculator, like right now, follow along with me. You'll see this is a picture of my phone's calculator, turned it sideways so I could get this stuff, and I think I hit this little button right here. I don't know if you can see my mouse, so I'll just circle it for you. It doesn't let me circle it for you, but it's in the top left. It's 2 arrows going in opposite directions. Below that, you have sine with superscript 1, cosine with superscript 1, and tangent with superscript 1. That's basically the same as saying 1 over sine is equal to sine over 1. And the same thing with cosine, sine, and tangent. Okay? So if you need to solve for an angle, you're going to need, and you only have one angle, you're going to need, there we go, you're going to need the inverse tangent. Okay? Here's the thing, is just one thing. If you see a question where you have a right triangle, and I'm giving you one angle, you know 2 of the angles, and they can only equal 180, so you can solve it from there. But let's look at this example. You're given the opposite side and the hypotenuse, and I'm asking you to determine theta and A. So we know we have the opposite over the hypotenuse, so we use sine. So, okay, S or sine equals opposite over hypotenuse. So sine of theta is equal to 5 over 10, which gives us sine of theta is equal to 0.5. So theta, right here, what we're essentially doing in this part here is we're dividing by sine on both sides. Okay? So that gives us the inverse of sine right here. So theta is equal to the inverse of sine times 0.5. And to be honest, when you're putting into your, I'm going to delete some stuff. When you're putting into your calculator, you should really remember, I haven't mentioned it yet, but you should really remember your order of operations. Your calculator might do this automatically, but I like using parentheses. It keeps everything nice and neat, because if you don't keep it too neat, you can kind of confuse yourself a bit, and then you get the wrong answers because your order of operations is all messed up. Okay, so I would have put a parentheses there. I even do it when I'm looking at the actual equations itself. Okay, so in this class, you're required to have all answers in meters unless otherwise noted. This means you may have to convert your final answer. All answers in this class must also have 3 significant figures and the proper units listed next to them. This means, are they in meters, centimeters, inches, miles, watts, joules? We'll get to that in a little bit. But that we need both correct significant figures and proper units. So these right here, these are our examples. Either it's 10 degrees and h equals 57 meters. Okay, determine O and H. These are just examples for you guys to work on. I will not do them, but work on these. They'll be very, very useful when you start working on your exam questions, maybe even the assignment coming up. Knowing this stuff will be very useful. If you need a refresher, once again, into trigonometry, even basic algebra, if you go on, you can go to khanacademy.org to look at the stuff. You can also just go on YouTube, type in Khan Academy basic trigonometry rules. That whole playlist, the first 2 videos is what you'll need, but I'd suggest just watching the whole playlist. Who knows, you might learn something whole reason you're in school. Okay, so I hope this helped. Once again, if you guys have watched this entire thing and you still are not sure on a lot of this stuff, feel free to email me. We'll have our Zoom meeting on Friday, and that's the perfect time to answer these questions. I can help you with all of this stuff. All right, hope you guys are having a good day. Goodbye.